Welcome to the Tech Study channel. In the previous class, we have seen sixth important question and its answer of Tribuli subject. So, in this class, I will explain seventh important question and its answer. Okay. So, seventh question is relationship between alpha, beta, gamma of a transistor. So, first we will see what is transistor. Then So, transistor, a fundamental semiconductor device used to switch or amplify electronic signal or power. Okay. So, amplifying means increasing strength of the input signal. Okay. And switching means switching on or switching off. Okay. So, the diagram is a tiny transistor with three terminals: emitter, base, and collector. So transistors are categorized by whether they are controlled by input current or input voltage. So if they are controlled by input current, then they are called current control device. Example, BJT, bipolar junction transistor. And if they are controlled by uh, input voltage, then they are called voltage control devices. Example, FET means field effect transistor. So in this class we will see only BJT because the CB configurations and alpha beta gamma relations are related to the BJT only. Okay. Then what is BJT? Means a device where a small current at one terminal controls a much larger current flowing through the other two. So then there are two types of BJTs: PNP BJT and NPN BJT. So PNP BJT means it contains two p-type materials. One is they are collector and emitter, and one n-type material, that is base. And NPN BJT contains two n-type materials, which are collector and emitter, and one p-type material, which is base. So in the circuit we represent like this. Okay. Then arrow mark indicates the flow of the current. Here emitter arrow mark indicates the flow of current. And then we will see what is emitter, base, collector, and doping. So then emitter supplies charge carriers, electrons or holes, into the base, which is here. Emitter is here. It supplies charge carriers into the base. Okay. Means the current direction will be in opposite direction. The charges are moving from emitter to base. So the current is flowing from here to here. Okay. Base to emitter. So then it is a heavily doped base, controls flow of charges from the emitter to the collector. Here is the base, which controls the flow of charges from emitter to the collector. Okay, from emitter to through the base and to the collector. Okay, and it acts like a gate for the transistor. Okay, it is lightly doped, and collector collects the charge carriers provided by the emitter. Here is the collector which collects the charge carriers, like which is electrons or holes, provided by the emitter, which is through base only. Okay, and it is moderately doped. So why these are heavily, lightly, and moderately doped means, so to understand that, we have to know first what is doping. Doping means a process where a tiny amount of impurities are added to pure semiconductor crystal like silicon or germanium to make better at carrying electricity, because the pure semiconductors are poor conductors at room temperature. Okay, then doping is used. The doping is useful to introduce either extra electrons or holes to serve as charge carriers in the pure lattice or crystal, that is silicon or germanium. So doping is used to introduce or add extra electrons to the n-type material. Means here in this n-type materials are collector and emitter. So and or holes. In p-type material, doping, doping introduces extra holes. Okay, to serve as a charge carriers in the pure lattice or crystal, silicon or germanium. So then we will see why it is heavily, lightly, and moderately doped respectively. Because emitter is heavily doped to supply maximum carriers. So here, for example, in NPN transistor BJT, the collector and emitter are of n type. Means and emitter is of n type, so it is heavily doped. Means the extra the more amount of extra electrons are added to the emitter. Okay, so that it supplies maximum charge carriers to the base. Okay, then base is lightly doped and thin to minimize recombination of carriers. Here in NPN BJT, base is the p-type material. Okay, and it is saying that it is lightly doped and thin. It is lightly doped means less number of holes are added to the base. So so why it is lightly doped means, if it is heavily doped, then more number of means more amount of extra electrons are added to the base. So if the holes of base, there are majority of holes in the base, so the holes of base recombine with the electrons which is supplied by the emitter. So the current does not flow in the current does not flow from emitter to collector, but it is lost at the base due to recombination of holes and electrons. So that's why it is lightly doped instead of heavily doping. Okay. Then collector is moderately doped to handle high voltage or heat while collecting carriers. Okay. The collector function, what is the collector function? It collects the electrons from the base. So it is moderately doped. Collector is moderately doped, means average number of extra electrons are added to the collector, which is of n type, है ना? Then so to control the voltage or heat during collection, okay, it is already collecting. If the number of electrons are more, then the voltage and heat will be increases. So that's why heavily doping is rejected for the collector, and moderate, it is moderately doped. Okay. Then uh, we will see types of doping. So types of doping, we have two types of doping: n type doping and p-type doping. N-type doping example is when pentavalent elements, means which has 5 valence electrons, example phosphorus and arsenic, are added to a tetravalent element which has 4 valence electrons, example silicon lattice. Okay. The fifth electron can't participate in the covalent bonding, becoming a free electron available for conduction. So the material is with an excess of negative charge carriers, electrons. In this way, the n-type material is doped. And for p-type doping, example is trivalent elements which has 3 valence electrons, example boron and aluminium, are added to a tetravalent element which has 4 valence electrons, example silicon lattice. The impurity only has 3 electrons to bond with 4 neighboring silicon atoms, leaving a missing electron site known as a hole. Okay, so the material is with an excess of positive charged carriers, holes. Okay, in this way the p-type material is doped. Then we will see the transformer and transistor voltages, that are VC, VBA and VBC, are the voltages between terminals that determines the operating region, cutoff, active or saturation. Okay. So these are the terminal: base terminal, collector, emitter terminal and collector terminal. So these are the voltages between them, okay, which decide the operating region. Then what is VC? Voltage between collector and emitter. Here the voltage between collector and emitter, VC. So it is responsible for creating a strong electric field at the collector to attract the base electrons to attract the base electrons or charge carriers. Okay. Then VBE, it is the voltage between base and emitter. VBE, it is responsible for flow of electrons from emitter to base. Okay. And for silicon, active and saturation region, it must be 0.7 volt. Okay. Then VBC, voltage between base and collector, Resp- responsible for flow of electrons from base to collector. Okay. then then we have completed transformer BJT, types of BJT, EBC definition means electron base collector definitions, and doping and types of doping also, and transistor voltages also. So then we will see what BJT connections. So BJT connections are three. Three types of BJT connections are there: common base, common emitter, and common collector. So first, common base connection, that is, in this circuit arrangement, input input is applied between emitter and base. Okay, this is the base, emitter and base, and output is taken from collector and base. Here is the output, here is the input signal. Here base of the transistor is common to both input and output circuits. Here is the base of the transistor, which is common to input and output circuits. Okay, this is input circuit and this is output circuit. Okay, and hence the name is common base connection. The circuit shows emitter current IE, and IB base current, and IC collector current, and output is there, and signal is there, and VBE voltage is there, base emitter voltage, and VCB is there, means collector base voltage is there. The BJT is of type NPN. Okay, then we will see what are IC, IB, and IE currents. So IC current is the electrons that successfully survived the trip across the base and entered the collector. Okay, so here the electrons that successfully survived the trip across the base. Here is the emitter. The electrons always flows from emitter to base, we know. Okay, so the electrons successfully survived the trip across the base and entered the collector. Okay, means why we are saying here successfully survived means because base contains holes. So the electrons which is supplied by the emitter is entering into the base and does not recombining with holes of the base and reaching and entering the collector. So here we are saying successfully survived. Okay. Then IE, emitter current, the total budget of current electrons sent into the transistor. So the uh, total budget of the electrons sent into the transformer. Okay, from here it is sent. Then IB means base current, the small loss of charge carriers that fail to reach the collector and instead exit through the base terminal. So here we have to understand it. The small loss of charge carriers that fail to reach the collector, which means here the loss of electron charge carriers or electrons occurs at the base, okay, terminal, that are failed to reach the collector and instead exit through the base. Okay, so here the exiting reasons are three. So what are they? Means exit through the base, meaning when electrons enter the p-type base, when the emitter electrons enter into the p-type base from and they are minority carriers since the base has many holes. Okay, these electrons are minority carriers for the base. Okay, because base contains majority of holes. Okay, then first reason is a few electrons fall into these holes and disappear, and the electrons falls into this base holes and disappears, means electron hole recombination occurs. And the second reason is the base terminal is connected to the positive terminal of battery or source, this positive terminal. So here the base terminal is connected to positive terminal. So this positive terminal acts like a vacuum cleaner for electrons. So the so this base terminal acts like a vacuum cleaner for the electrons. Okay, then so it collects electrons from the base terminal. This positive terminal will collect the electrons from the base terminal. Okay, which results in the IB current. Okay, then we will see third reason, that when an electron in the base recombines with a hole, the base loses a hole and becomes slightly more negative. So this becomes slightly negative. Huh? To fix this and keep the base working, the battery pulls an electron out of the base terminal. Means it pulls the electron from the base terminal or pushes a hole in the emitter. Okay, in the emitter to maintain charge neutrality. So what is charge neutrality means is the state where a material or region has an equal number of positive and negative charges, resulting in a total net charge of zero. So base is going to be become negative, so it preventing from becoming negative by maintaining charge neutrality. Okay, then next we will see common emitter connection. In this circuit arrangement, input is applied between base and emitter, and output is taken from and collector and emitter. Okay, here the emitter of the transistor is common to both input and output circuits, and hence the name is common emitter connection. Next we will see common collector connection. Here the input is applied between base and collector, base and collector, base and collector, which is signal. Input is the signal, and output is taken between emitter and collector. Emitter and collector, emitter and collector. Here is the output. Okay, then here also we have voltage of VBE, means base emitter voltage, because it is connected between base and emitter terminal. And here we have VCE voltage, means collector and emitter voltage, because it is the voltage is connected between emitter and collector. And here we have VBC, base collector voltage, and VCE, collector emitter voltage. Okay, then we will see definitions of alpha, beta and gamma. So first, the definition of alpha is the current gaining common base configuration. Alpha is the current gaining common base configuration. So gaining formula is equals to output by input. Alpha is equals to output current by input current. When VCB, means voltage of collector and base, collector base voltage is with constant, is kept constant. So alpha is equals to IC by IE. So we have seen in the definition that it is the current gaining common base configuration. In the common base configuration diagram, we can see that output current and input current are, output current is IC and input current is IE, emitter current. Okay, to understand more clearly what is alpha, I have explained with example also. So we keep the collector base voltage VCB constant. Here VCB we are keeping constant. Okay, so we can also say that alpha is the ratio of change in collector current to the change in emitter current. Here is the collector current and emitter current. And or alpha measures collector current per unit emitter current. So here alpha measures collector current per unit emitter current. Okay, then for example, if 100 electrons enter the emitter, Here is the 100 electrons are there. So, and 98 reach the collector. Here is the 98 electrons are reached at the collector. Okay. So alpha is 0.98 because 98 by 100 what 0.98 only. Okay. So the fraction of budget of electrons of emitter that reached the destination C is alpha. Okay. The fraction of budget of electrons of emitter that reached the destination C is alpha. Without getting recombined with the base holes. Okay. Then we will see what is beta. Beta is the current gaining common emitter configuration. Here is the common emitter configuration, that is beta is equals to output by input, where Vc is constant, common emitter voltage is constant. Beta is equals to Ic by Ib, collector current by base current, which is considered as equation number 2. It is considered as equation number 1. And so here in case of beta, we keep the collector emitter voltage constant. As we have seen in the definition, that beta is the current gaining common emitter configuration. So we are looking into common emitter diagram. Okay. So we keep the collector emitter voltage constant. Here Vc is constant. The ratio of change in collector current to the change in base current is called beta. Here is the collector current and here is the base current. So in the diagrams we can observe current direction also. Then beta measures collector current per unit base current. As we know from the formula, it measures the collector current per unit base current. Okay. Then if we take example, if 100 electrons enter the emitter, if 100 electrons are entered the emitter, okay, then collector 98 electrons reach the destination, reach to the collector. Okay, here it is reached. So and at base 2 electrons exist through the base as the loss. So here 2 electrons are exit through the base as the loss. From where those 2 electrons comes from emitter. Okay, and 98 are passed to the collector. So in calculation, beta is equals to Ic by Ib, that is equals to 98 by 2 collector current here and base current here 2 electrons, that is equals to 49. So for every 1 electron that exits the base through the base, 49 electrons are allowed to reach the collector. Okay, have you understand? For every one electron means we can write 98 by 2, and for this statement we can write 49 by 1, means for every one electron that exists, that exits, not exist here, exit through the base, 42 electrons are allowed to reach the collector. Here is the, here the 100 electrons are entered in the emitter, and 98 are passed to the collector, and 2 are exit through the base. Okay, so we have substituted the in the calculation formula. Then for every one electron that exists through the base, 49 electrons are allowed to reach the collector from the base. Okay, it means if one electron is exits through the base, then 48 electrons are allowed to reach the collector. Okay, reach the collector from the base. Okay, then that's why the base is act as a gate. By moving just 2 electrons at the base, we have controlled a messy flow of 98 electrons at the collector. Then beta measures exactly how many more electrons get pulled for every one extra electron we send into the base. Okay, beta measures the how many more electrons get pulled into the collector for every one extra electron we send into the base. Okay, then we will see definition of gamma. Definition of gamma is the current gaining common collector configuration. So common collector combination, we have to see the diagram. So gamma is equals to output by input, where Vc is constant. Here also collector emitter is constant. Gamma is equals to emitter current by base current. It is considered as equation number 3. Then so we keep the collector emitter voltage constant. Here this Vc is kept constant. It is the ratio of change in emitter current to change in base current. Emitter current to change in base current. Okay, it gamma measures collector current per unit base current. As we know from the formula, it measures the emitter current per unit base current. For example, same example I have taken. So 100 electrons enters the emitter. Collector at collector 98 electrons reach the destination. So 98 electrons are reached here to the collector. Then base it two at base 2 electrons exist through the base. 2 electrons exist through the base as the loss. Okay. Then calculation is gamma is equals to IE by IB, that is equals to 100 by 2. Here is the emitter current 100 by 2, that is IB. Okay, that is equals to 50. For every 1 electron we sacrifice at the base, you get a total flow of 50 electrons moving through the emitter. So here for this statement we can write gamma is equals to 50 by 1. So Y means for every 1 electron we sacrifice at the base. So here the electrons are exited now through the base as a loss, recombined or pulled by the positive terminal. So we get a total flow of 50 electrons moving through the emitter. We get a total flow of 50 electrons moving through the emitter. Okay. Then gamma measures the total budget of electrons, means emitter current, relative to the base loss, which is IB current, base current. Then we will see first what is the relationship between alpha, beta and gamma. So here the relation between alpha, beta and gamma is derived from these above definitions, means equations 1, 2 and 3. Okay, first we will take first equation, alpha equation. Alpha is equals to IC by IE. If we rearrange it, IC is equals to alpha IE. Then according to the transistor equation, IE is equals to IB plus IC. Okay, then replacing IC in above equation, we have replaced this with this equation number 1. So we get IE is equals to IB plus alpha IE. Then we are taking the emitter current at one side. Then we will get IE minus alpha IE is equals to IB. We are taking IE common. 1 minus alpha is equals to IB. Dividing above equation with IC, we get IE by IC into 1 minus alpha is equals to IB by IC. Then we are reversing whole terms. Then we get here we get IB by IC becomes IC by IB, and IE by IC becomes IC by IE, and 1 minus alpha becomes 1 by 1 minus alpha. So here we get IC by IB means beta, we know from the definition, and IC by IE means alpha, we already know this. Then by 1 minus alpha as it is. Then we are adding 1 both sides. Then we get beta plus 1 is equals to alpha by 1 minus alpha of plus 1. Then we are taking denominator common for these two terms. Then we get 1 into alpha 1, and minus alpha into 1 minus alpha. So denominator as it is 1 minus alpha. So that will be equals to alpha cancel, plus alpha minus alpha cancel, then we get beta plus 1 is equals to 1 by 1 minus alpha. So from equation 3, then we are taking equation number 3. So gamma is equals to gamma is equals to collector emitter current by base current. So by transistor equation, IE is equals to IB plus IC. So we are rearranging it. IB is equals to IE minus IC. Then this transistor equation we are substituting in gamma equation. So in place of IB, so IE by IE minus IC, and we are inversing these both terms, then we get 1 by gamma is equals to IE minus IC by IE. If we slip this denominator, we split this in denominator, we get IE by IE minus IC by IE. So it cancels, we get 1 minus IC by IE. So what is IC by IE? It is alpha. So we have written 1 minus alpha. Then we got the 1 by gamma as 1 minus alpha. If we inverse it, then we get gamma is equals to 1 by 1 minus alpha. We obtained this term earlier also, so which is equals to beta plus 1. So here we are adding it, 1 plus beta. So it is the relation between gamma, alpha and beta, means alpha, beta and gamma. So we are checking this equation by our example, that is 100 electrons, 98 and 2 electrons for emitter, collector and base respectively. So gamma, what we have obtained here, gamma we obtained 50. So we are substituting here, and 1 by 1 minus alpha. Earlier what we have got, alpha, here we got alpha is 0.98. So we are substituting here 1 by 1 minus 0.98, that is equals to 1 plus 49. Beta means 49. Here we get 49. Beta is equals to 49. Then if we calculate this, we get 50, and 1 plus 49 also 50. So this relationship is verified for this example. Okay. Then we will see advantages of alpha. Means common base connection. It offers high voltage gain. And advantages of beta, common emitter connection, highest power gain. It offers highest power gain. And advantages of gamma means common collector connection. It provides very high input resistance. Okay. So that's it for today's class. If you feel this video is helpful, then share, like and subscribe and comment. I will see you in the next class. Thank you. Bye.